Socratic Math Tutor here. So this is part 2A in a series about mathematical fundamentals, and today we're going to look at some really nice techniques for computing domains and ranges. One of them is well known, but for some reason it's mainly taught at a university level. I have no idea why. And for the other, I've actually never seen it taught in any context, and I'd probably describe it as semi-secret. And that's actually the one we're going to start with. So technique 1 is called finding the domain using expression in set patterns. So let's see how it works. So suppose the question says find the domain of f of x equals some awful combination of things, so we might have fraction here, we'll get a log going, get a linear term going inside the log. That's too simple, so we'll put something there. Let's get a 17 going. Let's go here with a square root. Subtract 5, and let's add 50 here. And you're looking at this and you're like, how am I meant to do that? I don't know how to work that out. Okay, you can totally work this out. This is not a hard problem. So step 1 is just to write f of x is an element of the real line. And that's because we're trying to write a constraint on x, expressing that x is an element of the domain of f. But another way of saying that is just that f applied to the number x is a well-defined real number. So that's your first line, and theoretically your second line should involve just grabbing this big awful thing and just putting it in here in place of f of x. So then we write this big awful thing is an element of the real line. But there's really no reason to do that extra step. I mean, this expression is a sum of two things, and each of those things needs to separately make sense and be a real number in order for f of x to be a real number. Okay, so we can skip a step, we can get rid of all this, get rid of that, and I'm just going to grab this fraction and write it here. And then I'm going to write this fraction and put it here. And as long as both these fractions are well-defined real numbers, their sum will be 2, so f of x will be a real number. And of course, this fraction is going to make sense and it's going to be a well-defined number if and only if the denominator is a real number, with exactly one caveat. It's not allowed to be 0. We're not allowed to divide by 0. And in a similar way, this fraction is going to make sense as long as the denominator makes sense and isn't 0. So I'm going to delete 0 from the real line. And so this first line is equivalent to this pair of conditions. As long as these are both true, this will be true, and x will be an element of the domain of f. So let's go ahead and call these something. So we'll call this alpha, and we'll call this beta. And so we can work on alpha and beta separately, and then put our answers together at the end. So let's focus in on alpha first. So alpha is equivalent to, and I'm going to copy out this line with one change. So we'll just take this -1, and we'll move it over. It becomes a +1. And so we get log to the base e of this stuff is an element of, and now I just add 1 to this point. Now let's do e to the power of both sides. On the left-hand side, it knocks out our log. On the right-hand side, we need to know what e to the power of the real line minus this point is, right? So e to the power of any real number is always a positive number. So we get this interval. And of course, we really don't want this expression to equal 1, because then we're going to get problems with this fraction. So we need to delete e to the power of 1, which is just e. Okay, so let's subtract 3 from both sides. This interval needs to move left 3 because we're subtracting 3. We also need to subtract 3 from this point we're deleting to keep it in the same spot relative to the rest of the interval. And then we just divide through by 2. Okay, and I apologize for this mouse cursor that suddenly appeared here. I had to re-record this bit, so I'm actually drawing now on a print screen of the previous image. So hopefully that's not too confusing. Let's go ahead and compute beta. So beta is equivalent to, and I'm going to rewrite this line, but we'll subtract 50 from both sides. Okay, so this next step is a little tricky. We're going to square both sides. We get 2x minus 5 on the left. On the right, we're going to ask ourselves, what is the real line squared? Or in other words, what numbers can be obtained as squares of real numbers? And of course, from the graph of x squared, that should be pretty clear. So if we square any point on the x-axis, the result will be either positive or 0. And so here we're going to put 0 through to infinity. And it's tempting to say, okay, let's delete the square of negative 50. So let's delete 2,500. But this actually turns out not to be correct. And I actually don't want to explain why that's the case just yet. So, I mean, we could draw a graph and just try and talk it out using the graph, but I actually don't want to do that. And the reason is because a little bit later in this video, there's going to be an interlude where we talk about the relevant concepts. And once we've got those concepts in our toolkit, then it's going to be a lot easier to understand why this bit at the end really isn't meant to be there. And by the way, this is sort of the first hint that doing the same thing to both sides doesn't necessarily work out. So we'll look at that in more detail in the interlude. Okay, let's go on. So I'm going to add 5 to both sides, get 2x in 5 through to infinity, and then we'll divide through by 2. So x is an element of 5 over 2 through to infinity. Okay, now I want to go further down, but I've run out of space. So because this is just a print screen, we'll continue here. So the original condition is equivalent to alpha and beta both being true, which is equivalent to saying x is in here and also in here. Or in other words, x is an element of the intersection. And if you draw a diagram, you'll see that this simplifies to 5 over 2 through to infinity. And the reason for that is basically that because negative 3 on 2 is strictly smaller than 5 over 2, well, that means this interval actually contains more points than this interval. So when we intersect them, we just get this interval on the right. And that's why it's appearing here. And the reason we don't need to delete this point is because e minus 3 is negative, right? E is approximately 2.71. The numerator is negative, and therefore this point is negative. And this interval contains no negative numbers. So deleting this point has absolutely no effect. Long story short, I think drawing a diagram is probably the best way to simplify these kinds of expressions, but feel free to use whatever approach you're most comfortable with. In any event, what we've learned is that the domain of f is the interval from 5 over 2 through to infinity. So we've swept a few things under the rug, but that's technique 1, and that lets you find the domain of potentially a very complicated function. There's other competing techniques out there for doing this kind of thing, but they're nowhere near as systematic. And so the really nice thing about this approach is that it scales really nicely as the complexity of the problem increases. Okay, so a few concluding remarks. Firstly, this concept of find the domain, it doesn't really make much sense. For example, suppose f of x equals 1 on x. Okay, find the domain. Well, the domain could be just about anything. I mean, it could be r delete 0. That might be the domain. I guess that's probably what the teacher wants, or the textbook wants, or the examiner wants if they ask this question. But I mean, really, it doesn't have to be. So it could be a proper subset. It could be the half-open interval from 1 to 5. It could be the empty set. It could be one of any number of different things. Now, sometimes they try and get around this problem by putting the word implied in here. So find the implied domain. So I guess this is supposed to mean, okay, find the largest domain that's actually reasonable. But I still really don't like this style of question, or at least this phrasing of this style of question, because the concept of what's reasonable is subjective. And it's really hard to convey systematic techniques, like the technique we just looked for, if what we're trying to do is solve a purely subjective or otherwise poorly posed problem. And so instead of saying find the domain, the solution is really to ask the student to find the corange. And if you don't know what I mean by the words corange or partial function, I recommend going back to the first video. I defined all these terms. I really started at the beginning and bent over backwards to make every little detail as clear as possible. And so I strongly recommend watching it. In any event, what we should be doing in this kind of context is actually providing the domain. The domain in this context is the entire real line. F is not a total function on the real line, but it is a partial function. Let's put par there. And so really this is the question we should be asking. Assuming that f is a partial function, with domain the real line and codomain the real line, and assuming that it's defined by this formula, what is the corange of f? That's the real question. Okay, so the second comment is that we're not really doing things to both sides. So for example, remember when we had that line, log 2x plus 3 is an element of the real line delete 1? And if you'll recall, I said at the time, well, let's do e to the power of both sides, because that's going to knock out the log to the base e. And the simple truth of the matter is that that was kind of an oversimplification. It was a little lie just to get us through the technique, and then I was going to talk it out at the end. And so let's go ahead and do that. What's wrong with doing e to the power of both sides? Well, the first thing is that the algebra doesn't even really work. So if we do e to the power of log of this is an element of e to the power of r delete 1, well, the right-hand side works just fine. This is just this interval with e deleted. But if you think about it, you'll see that actually the left-hand side doesn't simplify properly. So we can't just write 2x plus 3 here because there's another case, right? So if x is less than or equal to 0, this is actually the empty set. And that's because all we knew ahead of time was that x was a real number. Now you may say, well, hang on, we knew more than that. We had an assumption that x is an element of the corange of f, and we were manipulating that assumption. But actually, it was never an assumption. I mean, we were definitely manipulating it, but we weren't assuming it. And the reason is because we wanted bidirectional implications, right? So, for example, this is meant to be equivalent to this, which is equivalent to this, which is equivalent to the previous line. But our only assumption on the table was actually just x is an element of the real line. And so all we can really say is that this, let's call it u, this is a real number because, you know, x is a real number, and therefore 2x plus 3 is also a real number. And so all we can really do is use the formula e to the power of log to the base e of u equals u if u is positive, and the empty set if u is not positive. And if you're wondering why the empty set features here, basically it's because if u is not positive, then u will not be an element of the corange of log to the base e. More generally, this kind of stuff is explained in the previous video. And so unfortunately, this both sides stuff doesn't really work because, well, one reason is the formulae just get too complicated, right? So this is way too complicated, and we really just want 2x plus 3 there. The other problem with the both sides rule is that this bidirectional implication may turn out not to be bidirectional. Sometimes it'll just be a forwards implication. And the reason is basically that if a equals b, well, we can always conclude that f of a equals f of b, but we can't necessarily go back the other way. We can if f is an injection, but not every function is an injection. So for example, if we're squaring both sides, the backwards direction might not work. And I just want to emphasize at this point that all the steps we did to solve the problem we were just looking at, all those steps were correct, but the actual verbal justifications I gave for some of the steps were a bit simplistic. Okay, because I kept invoking the both sides rule, which is a good heuristic, but properly speaking, it's not really the correct way of justifying each step, because of these two problems. So what we're going to do is we're going to have an interlude here about the concepts of image and preimage that were discussed in the previous video, but now we need to go a little bit deeper. And so it turns out that once we've explored those concepts enough, the finer points of the technique we just saw are really just going to fall into place. And furthermore, the next technique we're going to look at, which is all about finding ranges, also depends on images and preimages. So this is a really logical place to put the interlude. Okay, so I'm drawing up an example relation that we can use to illustrate the concepts of image and preimage at a higher level of generality than we did in the previous video. And this relation I'm drawing happens to be a partial function, so I've called it f, but most of this discussion makes sense for any relation. And remember, we said in that video that the image of a point on the left, such as x1, is the set of all points on the right with a line segment to x1. So the image of x1 onto f in this context would be y1. Okay, and because this is a singleton set, we can usually conflate this with just y1. Unhappy face here to indicate that every so often that doesn't work, as explained in the previous video. And so now I want to ask, what is the image of not a single point, but rather a set of points, like x1, x2. And so this is one of those cases where the obvious definition is actually the correct definition. So in particular, the image of this set under F is going to be the set of all points on the right-hand side that have a line segment to at least one of these points in the set. So F of the set x1, x2 is still just the singleton set y1, and you can usually conflate that with y1. And of course, if we include x3 in here, well, now we get both of these. Okay, in a similar way, the image of x2, x3 is going to be both these points. So F of x2, x3 equals the set y1, y2. Okay, let's give ourselves a little more space. So up here, I'm going to put the definition of the image of a subset A of the domain. And if you have enough mathematical maturity to read that, that's awesome. If not, I just want you guys to have an intuitive understanding of the concept. We're just basically taking a subset from the left set and pushing it to the right set, and we're doing that by following along all the line segments incident to points in the original set. And although I've written F here, this definition actually works for any relation. Now, in a dual way, we can also take the preimage of a subset of the codomain. There's the definition. Once again, the intuition is just that we follow line segments to the other side, and in that way we can turn a subset of the codomain into a subset of the domain. And it turns out that these two constructions have a lot to do with ranges and coranges. Case in point, have a look at this set. This is the domain of F. Let's take the image of the domain under F. We'll get this set. This is the range of F. And so we learn that the image of the domain of F is always the range. And in a similar way, we can start off with this set. This is the codomain. And when we take the preimage under F, we get this set, which I'm calling the corange. But you can think of that as sort of the quote-unquote implied domain. So F preimage of the codomain is the corange. And actually, this is the formula we just used to find the corange of that complicated function we were looking at. So remember how our first line was f of x in R? Well, this was just meant to express that x is in the corange of f. So really, we should have started by writing that, x in corange of f, and then of course you apply this equation. So we replace the corange of f with the preimage of its codomain. So the next line is x in, and instead of corange, I'll write preimage of the codomain of f. And then on the line after that, of course, we get this, simply by shuffling the f preimage over, and it becomes an f image on the other side. And so therefore, all of these lines are equivalent, and we can proceed by equivalences to solve the rest of the problem. And so really, to make this technique work, all we needed was firstly this line, and you can almost think of this as like the definition of the corange. So this is almost like a definition. And the other thing we needed was the ability to convert between these two lines. So let's call this equivalence the shuffle law, since we're basically shuffling f around the set membership symbol. And so it turns out that the correct way of justifying the steps in technique 1 is not to do things to both sides, it's really just to repeatedly invoke this law, the shuffle law. For example, remember this line? So we were trying to solve log to the base e of 2x plus 3 minus 1 is an element of r delete 0. So really we should think of this as the subtracting 1 function, so I'll just write box minus 1 for that, applied to log to the base e of 2x plus 3. And so the left-hand side here is the image of this stuff under the subtraction by 1 function. And so using the shuffle law, we can move the box minus 1 to the other side, keeping in mind that images on the left become preimages on the right. And it's probably not going to be too shocking if I say that the preimage under box minus 1 of a set is the same thing as the image under box plus 1. And so that's how we get r delete 1 on the right-hand side. Okay, so no use of the both sides rule. We only used the shuffle law. And of course, you can leave out most of these steps in your working. I mean, here's line 1, here's line 2. That's really all you need, just 2 lines. Okay, so let's keep going. Let's now move log to the base e to the other side, again invoking the shuffle law. Notice that here we get exactly what we want. We get 2x plus 3. We do not get a complicated expression that looks something like this. This is progress. And it's probably not too shocking to say that the preimage under log to the base e is just e to the power of. And as we saw before, this is just the positive numbers with e deleted. Okay, now I want to talk about squares and square roots as well before we move on to the next topic. But there's one more issue that's worth addressing here, and that's the question of how you do this step and how you do this step. So in both cases, we seem to be computing the image of b delete a under a function, or more generally a partial function. And the question is really, when can this be written as f of b delete f of a? Because that's what we used here, and that's also what we used here. And go ahead and hit the pause button if you need more time to process that. So let's spend a moment trying to understand the interactions between set operations, like intersection, union, and set difference, and images and preimages. So it turns out that unions are the best. Now, I'm not necessarily saying unions are the best. Margaret Thatcher certainly doesn't think they're the best, but according to mathematics, they're quite simply the best. And the reason for that is basically that if we take any two subsets, call them A0 and A1, of the domain of any relation, and take the union of them, and then apply that relation to that union, the result will simply be the image of A0 union the image of A1. And a similar statement holds for preimages. Take any two subsets, B0 and B1, of the codomain, then take the preimage of their union, and the result will be the preimage of the first one, union the preimage of the second one. And these formulae work for any relation whatsoever. You don't have to check that it's a function, you don't have to check any other conditions, it always just works. Okay, and I'll just move this over. I feel like they're a bit cramped, so let's spread out our formulae a little more. Okay, also, under this heading of unions are the best, let's also say something about the empty set, because the empty set is actually the empty union, so it really goes under this heading. And the formula is really as simple as you'd like it to be. The image of the empty set is empty, and the preimage of the empty set is always empty. Couldn't be simpler, right? Now, on the other hand, intersections and set differences are a little bit more complicated. So let's have a look at an example. So here's the set with 2 points. We'll call them x2 and x1. And here's a set on the right with 1 point. Call it y1. And let's just map both these points on the left to the same point on the right. We'll call that f. I'll just center it a little bit to make it look a bit more appealing. And now let's define a couple of singleton sets. So A1 will have x1 as its sole element, and A2 is going to have x2 as its sole element. Okay, and so obviously f of A2 is this singleton set, and this is also f of A1. Okay, so what does this actually teach us? Well, as it turns out, it actually teaches us quite a lot. So let's go ahead on the left here and just compute the image of A1 intersection A2. You can see here that A1 and A2 share no elements, and so their intersection is empty, and therefore the image of that is also empty. Now, on the other hand, if we take the image of A1, we get this singleton set. The image of A2 is the exact same singleton set, and therefore the image of A1 intersection the image of A2 is precisely that singleton set. Notice that these are different. Okay, in a similar way, we can take the image of A1, delete A2. So A1's all the way up here, A2 has nothing to do with it. They don't share any elements. So if we start with A1 and delete all these points, well, we just get A1 back. So then when we take the image, we get this singleton set. Now, on the other hand, if we take images first, well, the image of A1 is this singleton, the image of A2 is also this singleton, and therefore when we do this set difference, we end up with the empty set. So to address this discrepancy and this discrepancy, we're going to use the following theorem. If a relation R with domain equal to any set you like, we'll call it capital X, and codomain equal to any set you like, we'll call it capital Y, is codeterministic, right? So in this case, good things happen. So the image of A1 intersection A2 is always going to be the intersection of the images. This is for any two subsets A1 and A2 of the domain, capital X, and the same can be said of set differences, as long as we have this codeterminism. And in practice, that's going to mean that we'll want an injective function on our domain, or possibly an injective partial function on our domain. And graphically speaking, this amounts to a certain version of the horizontal line test. And in particular, we need to use that to check that preimages of points on the y-axis have at most one element. So let's have a look at some practical examples. Okay, so let's start off by drawing a graph of e to the x. Looks a little like this. And notice that this passes the horizontal line test, right? So for this line, we intersect in one point. That's because the height of the line is positive. For height 0 or height negative, we don't intersect at all. And so in general, we can say that horizontal lines intersect this curve in at most one point. Hence, the e to the power of function is injective. And so this explains our computation from earlier, right? So we had e to the power of r delete 1. And basically, we want to break this up as e to the power of r delete e to the power of 1. And we can because of injectivity of e to the power of, and then we just work out each set separately. Let's now look at another example. So in particular, I want to have a look at box squared, or in other words, the squaring function. And lo and behold, the horizontal line test for codeterminism is not passed, because we're intersecting here in 2 points. So therefore, if we look at the set r delete 1, and we try and square that, well, it's not true that this is the real line squared, delete 1 squared. This is wrong. And that should sort of make sense. After all, if we remove positive 1 from our set of inputs, it doesn't actually make any difference, because we can get the same output by feeding in negative 1. And so therefore we don't need to delete this point from our output set, because we can still achieve the same output by a different value in the input set. So therefore this part shouldn't be there. And therefore this equals sign is now correct. Okay, but this raises another question. So what's the actual formula for dealing with something like this, in which we're deleting a set that's not big enough to result in the deletion of the entire image of that set? Well, there is a formula. We're not going to deal with it today because it takes us too far afield from our goal, which is to solve high school and early university math problems. And so for our purposes here, what I want to do instead is something just a little bit more basic. So in particular, we're going to look at this graph, and we're going to look at intervals on which it's injective, right? So on the right-hand side of the y-axis, it's injective. On the left-hand side, it's injective. And therefore, we can break this up into 2 cases, and the image will be the union of those 2 cases. Okay, let's move everything up a bit to give ourselves a little more space. And down here, I'll just write the facts we're going to use. We're going to use that box squared is injective on the positive numbers union 0. And it's also injective on the negative numbers union 0. So using that, we can do this computation as follows. Okay, so we're trying to compute this bit, put it up here. And on step 1, we're going to break up r delete 1 as the negative numbers union 0, union the positive numbers union 0 with 1 deleted. And this whole thing needs to be squared. Now remember earlier we talked about how unions are the best. Not according to Margaret Thatcher, not necessarily according to me, but according to mathematics, we can break this up, and so this is the square of the first set union the square of the second set. Okay, so for this part we need to ask the question, what numbers can we get by squaring numbers that are 0 or less? And the answer is all the numbers that are 0 or more. And then for this part, we can break it up as 2 different bits. And of course, this part just involves deleting 1 squared, which is 1. So I'll get rid of that 2 there. And this part requires us to ask, well, what numbers can we get by squaring numbers that are 0 or more? And obviously, it's the set of all numbers that are 0 or more. So I can get rid of that square. So now we've got an expression involving this interval, including 0 and going to positive infinity, and we're taking the union of that with the same thing, but with 1 point deleted. And so that's just this guy, it's the larger of the 2. And so you'll notice here that we don't need to delete 1 squared, because even though we're deleting it here, we have another contribution over here that's covering that point that we're missing over here, reflecting the fact that this +1 is covered by this -1 over here. So with that in mind, let's finally go back and have a look at those square roots. We had the square root of 2x minus 5 is an element of r delete -50. That was from the problem we looked at. And I want to look at a similar problem as well. So imagine we have the same expression on the left, but this time let's delete +50. So what happens? Well, let's start off over here. We'll move the square root to the other side using the shuffle law. So on the right-hand side, I get box squared applied to all of this stuff. And we have to keep in mind how square root was obtained. So it was obtained by taking the squaring function, restricting to the positive numbers union 0, and then swapping x and y, effectively swapping inputs and outputs. So therefore on the right-hand side, we don't actually have squaring, we have squaring restricted to this corange. So for our next line, the left-hand side remains the same. On the right-hand side, we need to do box squared restricted to this set applied to the real line, and we also need to do box squared restricted to this set applied to this part. Why is it that we can break things up like that? Well, box squared is injective on this interval. So let's ask the question. Suppose I start with the real number. If it's not in this interval, I just throw it away. If it is in this interval, I square it. Well, what numbers can I get out of this process? Well, obviously it's this entire set. If that's not clear to you, go ahead and draw a graph, and it should become pretty self-evident. Okay, so now we need to delete box squared restricted to this interval applied to this set, but this set is not in the corange of this, because we've restricted the corange to this interval, which doesn't have any negative numbers. And therefore, when we apply this to this set, we actually get the empty set. And so there's really nothing we need to delete on the right-hand side. We've just got this entire interval. And remember, when we actually solved the problem, I basically just jumped all the way from this top line to this line. And recall in particular that earlier on, I was having trouble explaining why this element is not supposed to be deleted from this interval. Well, now you know. It's because when we shuffle this square root over, we get box squared restricted to this interval, and -50 is not in that interval. And so therefore, it's incorrect to delete this point. And as long as we don't, the top line here will be equivalent to this line. Now over here, I've replaced -50 with +50, so let's make sure we understand how this changes things. The first step is the same. The next step is similar, but instead of empty set here, we're going to get 50 squared, and that's because 50 is in this interval. And then on the last line, we'll just simplify. And once again, I recommend just writing this first line, and then this last line. The intermediate steps essentially just need to occur in your head by thinking about what the graphs look like and what intervals we're restricting to. So that's technique 1. I hope you guys have enjoyed this so far. We're actually nearly done because technique 2, which we're about to look at, basically leverages the exact same ideas, so you practically know how to do it already. Okay, so technique 2 is called finding the range using the formula range of f equals f applied to the domain of f. Now, unlike the previous technique, this one is not at all secret. It's a standard technique taught at a university level, but for some reason it's not really taught in high school very often, and so I think you guys are going to get a lot out of it. Okay, so suppose we're given a function, and I've just written down a quadratic here as a nice easy example. It's not a coincidence that it's in turning point form. This actually makes our job easier. And so we'll take this as a kind of simple example, and we'll look at harder examples later. So the task is to find the range of f. So in particular, the range of f, according to the formula we just saw, is f applied to the domain of f, but of course the domain of f in this context is given. In fact, the domain of any function should be given. It should only be the corange we're asked to find. In any event, we have range of f equals f of its domain, which equals 3 times the real line minus 1 squared plus 5. So first we need to take the image of the real line under the subtraction by 1 function. That gets us the whole real line. Then we square that, and we just get the positive numbers union 0. Multiply that by 3, it doesn't change anything. And then we just add 5. Now there's something important here that you need to understand. This step here, from this line down to this line, this only works because there's exactly one mention of x here. Okay, so let's have a look at what goes wrong if this condition isn't satisfied. So if we take the formula that defines f of x and we expand out the brackets, we find that f of x equals 3x squared minus 6x plus 8. You can check that yourself, but for the purposes of this illustration, the process of expanding this out just isn't that important. So what I really want to do is compute f of r using this formula. Remember, up here we used range of f equals f of r to actually get our answer, and that was with this formula, which only mentions x once, but what happens if we use this formula, which mentions it twice, here and here? Well, we get 3 times r squared, which is this interval, minus 6 times r, plus 8. Now, if we scale this interval by 3, it doesn't change the interval. If we scale the real line by negative 6, we still end up with a real line. And adding 8 doesn't have any effect, so let's just leave off the adding 8, because if you move the real line by 8 to the right, you still end up with the entire real line. Okay, and now we've got to add this interval with this interval. And so the question has to be asked, what set of numbers can be obtained by first choosing a real number and then choosing a positive or 0 number to add to it? And the answer is we can get every number in that way. And so notice that this is not the same as this. These are not the same set. And in particular, what happened here was that the kind of quote-unquote inference from this line to this line was wrong. Okay, so plugging in an entire set in place of a variable, like we did here, only works if there's exactly one copy of the variable. And I think that's really important to remember. So if you want to apply this technique to finding the range of 3x squared minus 6x plus 8, for example, step 1 is to get it into turning point form. So for example, you can use completing the square, or you can just memorize the formula for the turning point form. Personally, I think that's a really great approach because then it's just one step. But whatever approach you use, you've got to make sure you've got it in a form in which there's only one copy of the variable. Okay, so to get started, we need to rewrite this formula in order that only one copy of x is involved. And to do that, we use polynomial long division. And in fact, because these numbers are small and because the degrees of these polynomials are small, it's actually very easy. I mean, we can just use algebra to do it. So I'm going to rewrite the numerator as x minus 1 minus 1. The denominator remains the same. And then we just break this up into 2 bits. So the first bit is just x minus 1 over x minus 1, which is 1. And the second bit is just 1 over x minus 1. Okay, so now we've got one variable in the rule for f. And so we can go ahead and compute the range just by sticking the domain in, which is this big ugly set. Okay, so the range of f equals f applied to its domain, which equals this expression with x replaced by this set. And to save us a line, I'm actually going to subtract 1 in this first step. So instead of writing this stuff minus 1 in the denominator, I'll just subtract 1 from this. So we've got 1 minus 1 over, and it's this subtract 1, so it's 1 through to infinity, delete 2, 3. Okay, so now we have to reciprocate this denominator. The relevant question is really, well, is 1 over box injective on this set? And the answer is yes, and that's because 1 over x looks like this, and this set we're looking at just starts at 1, it includes every number up to 2, but not including 2, every number between 2 and 3, not including 3, and then it goes through to infinity. Let's just put some labels and some arrows. Okay, and so notice that this graph passes the horizontal line test for codeterminism. For example, this line just intersects in one point. There is one specific line, namely y equals 0, that doesn't intersect the graph at all, but all that means is that 1 on box isn't surjective. And so therefore, we can break up this reciprocation into the reciprocal of this interval, delete the reciprocal of this set. And now we can work out each part separately. So 1 minus, okay, let's do set deletion here. 1 divided by this set is the set 1/3, 1/2. And the reason is basically that this set can be thought of as the union 2, union 3. And so because unions are the best, we really don't have to worry about injectivity here, we just do it. And notice there's kind of a flip, so the 2 ends up mapping to 1/2, which is actually bigger than 1/3, which is the result of reciprocating 3. So kind of that the 2 goes here and the 3 goes there. And that's because on the right-hand side of the y-axis, you can see that 1/x is actually a decreasing function. Actually, interestingly enough, this is decreasing on the left-hand side of the y-axis. Look at this, it gets lower and lower and lower. On the right-hand side of the y-axis, it's also decreasing, but actually the whole function can't be said to be a decreasing function because this point, for example, is lower than this point. So if we're jumping the y-axis, there's actually an increasing tendency. So 1/x is not a decreasing function, but is decreasing on the positive numbers, which is why we're getting this flip here. And that also explains how to compute this. We have to do a similar flip over here because we're decreasing on the positive numbers. So on the left-hand side, I'm going to reciprocate infinity, we get 0. On the right-hand side, we're going to reciprocate 1, we get 1. And at this point, we're nearly done. We just have to work out 1 minus this set. And if we graph 1 minus box, or in other words, if we graph y equals 1 minus x, we find that it looks like that. So it's a decreasing function. So because it's decreasing, we get injectivity for free. Every decreasing function is automatically injective. Okay, so decreasing implies injective. Of course, increasing also implies injective. The converse is not true, as we just saw. So 1/box is injective, but it's neither increasing nor decreasing, because when we jump the y-axis, it's increasing, and when we don't, it's decreasing. And so actually to go backwards from injectivity to conclude that a function is either decreasing or increasing is actually less straightforward. You need some conditions on the function, continuity, that kind of thing. But actually that doesn't matter for our purposes because we know y equals 1 on x is decreasing, so it has to be injective. And that tells us that we can break this up as 1 minus this set, delete 1 minus that set. So all right, equals, put a set deletion symbol here. Let's do this part first. So 1 minus 1/2 is 1/2. 1 minus 1/3 is 2/3. Notice once again we got the flip because it's decreasing. If it were increasing, there would be no flip, and these would be in the same order. But they've changed order from here because it's decreasing. And we'll do exactly the same thing here. So put a square bracket here, a round bracket here. 1 minus 0 is 1, so I'll put that with the round bracket. 1 minus 1 is 0, so I'll put that with the square bracket. And so there's our answer. The range of f is the half-open interval from 0 to 1 with 2 points deleted. So I hope you guys enjoyed this video. This particular one took me about a week to make. So if you enjoyed it and you got something out of it, don't hesitate to share with others who might also benefit from it. I'd love to get a few more subscribers and just a little more confirmation that these videos are actually helping people and that they're worth continuing to make. And don't forget to tune in for the next video, part 2b, in which we continue looking at secret and semi-secret techniques for finding domains and ranges, and we start getting calculus and limits involved. So I'll see you then.